This section will cover using kinematics graphs, in particular displacement time graphs and velocity time graphs, to describe motion in a straight line. So we're going to start by considering what the displacement time graph would look like for this journey on a bike. So we're going to have time along the horizontal axis and displacement along the vertical axis. So watch the journey first and then consider what the graph would look like. So pause the slide and have a go at sketching the displacement time graph for that journey. Okay, so here are the axes. We have time along the bottom, we have displacement up the side, and we're going to draw the graph as the journey goes on. So we can see that there were two sections where the bike was moving, this section here and this section here, and there was a section in the middle where the bike stopped, and at this point the gradient was zero because the displacement was not increasing or decreasing. Now do the same with this journey. So we're going to do that again, but with the graph. So we can see that initially the bike set off at a constant speed to the right, paused briefly, and then returned at a constant speed but faster to the left. So we can see that the faster section had a negative gradient because it was travelling in the reverse direction, and it also had a steeper gradient to show that it was travelling faster. We also had this section at the top where the displacement briefly stopped moving, the bike stopped moving, so therefore the gradient was zero. Now consider the graph for this journey. Think carefully about the direction here. Let's look at that again. So here we can see, because the bike started here in the middle, this is zero displacement. So when the cyclist was to the right of the initial starting point, we had a positive displacement. It then travelled back again. When it returned to the starting point, this is where the displacement was zero. And then as the cyclist continued to move, we then got a negative displacement to show that they were travelling to the left of the starting point. Now consider the graph for this journey. So let's look at that again. We can see the bike started from rest and increased its speed until it got to a maximum and then slowed down and stopped. So we can see here the speed was zero, the velocity was zero here. You can also see the velocity was zero here, and its velocity increased and then decreased. We're now going to consider a journey made by a cyclist and show his journey on a displacement time graph. So the cyclist leaves home and travels 2 kilometres in 5 minutes. He then waits for 3.5 minutes and then travels directly home, taking 8 minutes. So we're going to start with some axes here. The first section of the journey, which involves travelling 2 kilometres in 5 minutes, takes us to 5 minutes and 2 kilometres, so here. In this section of the journey, the cyclist waits, so the displacement does not change during that time. And in the final section, the cyclist travels home, taking 8 minutes to travel the 2 kilometres back home. We want to know what speed the cyclists travelled during the first part of the journey in kilometres per hour. So we can consider that they travelled 2 kilometres in 5 minutes. We need to work out how far they would travel in an hour. We know that there are 60 minutes in an hour, so we scale this up to give us 24 kilometres in 60 minutes. Travelling 24 kilometres in 60 minutes gives a speed of 24 kilometres per hour, because the cyclist travels 24 kilometres in 1 hour. We now want to know what the cyclist's speed is during the first part of the journey in metres per second. So for this, we can convert. We know that 2 kilometres is 2,000 metres, and we know that 5 minutes is 300 seconds. So we can calculate distance divided by time, and this works out as 6.6 recurring, or 6 2/3 metres per second. This means that they are travelling 6.23 metres in every 1 second. What does the gradient of this section of line tell us in terms of metres and seconds? Well, if we calculate the gradient here, we can see that in metres and seconds the gradient will be 6 2/3. This is because the gradient of a displacement time graph tells us the velocity. We now want to know what the cyclist's speed is during the final part of the journey in metres per second. So this time we know they travel 2 kilometres in 8 minutes. This is 2,000 kilometres in 840 seconds. If we divide the distance by the time, this gives us 4 1/6 metres per second. We now want to consider what the velocity of the cyclist is during this time. Now initially you might think that this is the same question. However, velocity also takes into account the direction the cyclist is travelling in. This is because velocity is a vector quantity, so we have to consider the direction as part of the answer. This means because the gradient is negative, the velocity would be negative 4 1/6 metres per second. So scalar quantities only have a magnitude, not a direction. This means that a scalar quantity will always be a positive number. Vector quantities give us a magnitude, so a size, and a direction. This means that vector quantities can be positive or negative. So to give you some examples of scalar and vector quantities, the speed of an object is a scalar quantity, so it will only have a positive value. It just tells you how fast they are travelling, but not what direction. However, the velocity will tell you how fast something is travelling, the magnitude, but also the direction they are travelling in, plus or minus. Similarly, the distance that something is will be given as a scalar, so we'll just have a positive direction, a positive solution. Whereas the displacement also takes into account direction, so displacement is a vector quantity and could be positive or negative. We have seen that the gradient of a displacement time graph gives the velocity. We can also use this formula. Velocity is the change in displacement divided by the change in time. SI units are a consistent system of international units that are used for measurements. These are the SI units that we will be using. For distance or displacement, we'll be using metres. This is a lowercase m. To measure time, we'll be using seconds, and this is a lowercase s. And for mass, we will use kilograms. We can use these 3 units to derive other units from them. So for example, we know that velocity is the change in displacement divided by the change in time. So using the units for displacement and time, we can see that the unit for velocity will be meters over seconds, which using the laws of indices can be written as ms to the minus 1. We're now going to consider the journey of a bike and sketch its velocity time graph. So this time we're going to have time along the horizontal axis and the velocity along the vertical axis. Remembering that the velocity is the speed, which also takes into account direction. So it can be positive or negative. We're going to assume that travelling from left to right in this situation is positive and that going from right to left is negative. So consider this first journey. We're now going to consider the same journey but with a velocity time graph. So we can see that initially the cyclist set off with a constant positive velocity. It then stopped, which meant that the velocity was 0 for this period of time. It then started again with a slower velocity, which gives us this line here. Remember that this was the displacement time graph for the same journey. So compare the different sections. Now we're going to consider the next journey. So to draw the velocity time graph, we can see that initially the cyclist had a constant positive velocity. It then briefly paused, so the velocity was 0, and then on its return journey the velocity was negative as it was travelling in the opposite direction. Remember that this was the displacement time graph for the same journey for comparison. Now consider this journey. Remember that you are considering the velocity here. You may want to pause the slide and try to sketch the velocity time graph first. And here is the same journey with a velocity time graph. So we can see the cyclist was initially travelling with a positive velocity in a constant speed, and then turned and returned faster with a negative velocity to the other side. This was the displacement time graph for that same journey. Now consider this journey and its velocity time graph. And again with the graph. So we can see that initially the velocity was 0 and it then increased. So for this section of the graph, the cyclist was accelerating, the velocity was getting higher. It was accelerating at a constant rate, which is why we have a straight line. Then, about halfway through the journey, the cyclist started to decelerate until eventually coming to rest. So the velocity was 0 again at the other end. Here is the displacement time graph for the same journey. We're now going to consider a situation where a cyclist leaves home, travels with a constant velocity of 8 meters per second for 12 minutes, and then travels home again for a further 20 minutes. We're going to show this information on a velocity time graph. You might want to pause the slide here and try to draw the graph yourself first. So here is the velocity time graph. Note that we've got time along the horizontal axis and velocity on the vertical axis, and also that we've labelled the axes with the units that we are using. So initially, the cyclist travels with a constant velocity for 12 minutes. We then need to have a section of the graph where they are travelling for 20 minutes to return home. However, we don't know what velocity the cyclist is taking. For this, we need to know how far the cyclist has travelled in the first section, so we can work out how fast they need to travel home in order to travel the same distance home. So we need to know how many metres the cyclist travelled in the first part of the journey. For this, we can use the formula. This is speed multiplied by time, which will give us displacement. Notice that this is also the area underneath the section of the graph. It's just the height times the base of the graph. So we know that the cyclist travelled 5,760 metres in that time. This is the distance that they will travel home in order to return to the same point. So we now need to know what velocity the cyclist will need to travel home in order to return to the same point. So for this, they're going to travel the same distance, and this time we can calculate the speed by calculating the distance divided by the time, remembering to convert the time into seconds as we are working in meters per second. So 5,670 meters is already in meters. However, 20 minutes will be 20 times 60 to give us the number of seconds travelled. This gives us a speed of 4.8 meters per second. Now, in order to return home, the cyclist will need to travel in the opposite direction, so we will need to use a velocity of negative 4.8. So we can now add this to the graph. Here you can see that we have a rectangle with the same area as this rectangle here, showing that the cyclist has travelled the same distance in both sections. In this case, the total distance travelled would be 5,760 plus another 5,760, so 11,520 metres. However, displacement would be 0, as we have a positive and a negative displacement which have cancelled out. This means the cyclist has returned to the same point. Given this velocity time graph for a journey, can we work out the total distance that was travelled? Well, we've already seen that the distance travelled is the area under the velocity time graph, and because this is a triangle, we can calculate it using half base times height. So we have half of 32 multiplied by 12. This gives us a total distance of 192 metres. In order for this to work, we need to make sure that the units are consistent. So in other words, we have to be using time in seconds, velocity in meters per second, and distance in meters. If any of these were not in these standard units, we would need to convert them first. What does the gradient of the line represent in this situation? We know that on a velocity time graph, it's the change in velocity which gives us the acceleration. So the rate of change of velocity is the gradient of the graph, which gives us the acceleration of the object. So to summarise, the gradient of a velocity time graph gives the acceleration of an object. Acceleration can also be calculated using change in velocity over change in time. Acceleration is a vector quantity, so it can be positive or negative. and it has these SI units. It can be calculated using velocity over time. We know velocity is calculated in meters per second and time is measured in seconds. So this gives us ms to the minus 2, or meters over second squared. This is usually pronounced as meters per second squared. We've also seen that the area under a velocity time graph gives the displacement of the object. If the area is above the time axis, it will be a positive displacement. If the area is under the time axis, we'll have a negative displacement. Now have a go at these 3 exercises using the examples and the information from the previous slides.